this lecture we will solve various example circuits, first order LTI circuits. This is our first example where we see how to deal with a ramp excitation. This is our circuit. Okay. This resistor is 1 ohm, this is 3 ohms. The inductance is 2 Henry. And we want to figure out the inductor current IL. Initially, there is no flux in the coil, or the inductor current is 0. And the input to this circuit is 10 RT volts. And remember, RT was the integral of step, or in other words, we have the ramp function T0, which is 0 for all negative times. And starting from t equals 0 onwards, the ramp, unit ramp, increases with slope 1. Here we have 10 RT, therefore the slope will be 10. Nevertheless, it's constant slope. 1, 10. Okay, this is our 10 RT. Okay, so let's obtain the differential equation, as it is the first step in almost all of our examples. And to obtain the differential equation, let's simplify the circuit a little bit. And by simplifying circuit, usually what we mean is we replace the one port seen by our dynamic component, be it a capacitor or an inductor, as in this case, with its either Norton equivalent circuit or Thevenin equivalent circuit. So therefore, for this case, let's work out using the Norton equivalent circuit. Okay. Now here we have 10 RT amps. This is 3 or 4 ohms. Okay, this guy, that guy, parallel. That's in resistance seen by the inductor, and we have the inductor here, 2 Henry. Now we will try to figure out IL. And initial condition is 0. Okay. So basically this thing here, to the left of this port, is the Norton equivalent circuit seen by the inductor, okay, in this circuit. So this is step 1, or perhaps step 0, that is simplifying the circuit so that we can obtain the differential equation more easily. So let's write down whatever we can write down. We can start from KCL. Okay, sum of 3 currents must equal 0. That is IL plus, okay, this current, which is VR over the resistance 3 over 4. What's VR? VR is VL, because everything is parallel. And what's inductor voltage for terminal equation? It's L DIL. Okay, so 2 DIL is the voltage that appears across the terminals of the resistor, divided by the resistance gives us the resistor current. And plus this current, which is minus 10 RT, okay, equals 0 by KCL. Therefore, for t greater than or equal to 0, we can replace 10 RT with simply 10 T. Okay. And then reorganizing the terms, we can write DIL plus 3 over 8 IL equals 15 over 4 T. So that's our first order differential equation. Clearly non-homogeneous because the right hand side is non-zero. So let's call this equation 1, differential equation. So whatever the solution is, it should satisfy that differential equation plus the initial condition constraint, IL0 equals 0. Now, since that's a non-homogeneous differential equation, the approach is such that we figure out the homogeneous solution, we figure out the particle solution, and we combine those two pieces. Now, the homogeneous solution has nothing to do with the input. Okay? You can always find the homogeneous solution by killing the input or the inputs in the circuit, and that would correspond to removing the right-hand side. Okay? And this equals 0. The solution of this equals 0 is what we call the homogeneous solution. The natural frequency is at -3/8, therefore the homogeneous solution is some constant times e to the -3/8t. Okay, e to the -3/8t is our homogeneous solution. And here the next question is, what's the particle solution? So far we have seen only two types of right-hand side or input. One of them was constant. Usually we dealt with constant. And whenever the right-hand side is constant, okay, particle solution, we said, inherits that form and also is constant. And how we figured out that constant is we plug in our candidate, okay, and obtain solution for a particular solution. Now in this case, by looking at the right-hand side, is something times t. The first guess perhaps would be that the particle solution will be something times t, okay, a times t, let's say. But it turns out that in general it doesn't work out. So we have to interpret what we mean by form of the input, okay. So the form of this input is such that it turns out that it's the right way to interpret the form is this has a constant slope. Okay, so the particle solution must be of the form such that it has constant slope. So the particle solution that has constant slope means we're talking about a polynomial of degree 1. Okay, so therefore the particle solution must have this form. It's determined by two unknowns, A and B. So we have two unknowns, A and B, from the particle solution. We have one unknown, K, from the homogeneous solution. And figuring out all those three unknowns will allow us to write down the complete solution. Okay, so let's begin by working on A and B. So what's A and B? Or in other words, what's the particular solution? So the particular solution, as always, has nothing to do with initial condition, and it can be obtained directly from the differential equation. Therefore, IP should solve equation 1. Hence, let's plug in our candidate into the differential equation. DIL, okay, plus 3/8 IL, and now by IL we mean IP, the particular solution, must equal the right hand side, 15/4t. Okay, so differentiating this will remove A because A is constant and will leave us with B. So what we have is B plus 3/8 times that equals 15/4t. So we can write that form. We have B constant term coming from here and 3/8 A constant term coming from here, plus we have 3B/8t, okay, the t term equals 15/4t. Now this equation should hold for all times, and from that it's clear that this constant term must be 0, and this 3B/8 must be 15/4. So this gives us B, and then once B is known, this equation gives us A. So the particle solution is figure it out. Okay, so B equals 10. Okay, and then A equals what? Minus 27 almost. Then IPT is minus 8 over 3 plus 10T Fs. Okay, so we figured out the particle solution. How to find K, our less unknown. How to find K is through what we do as usual, that we combine homogeneous solution and particle solution, write down the complete solution, and once we write down the complete solution, we subject that solution to the initial condition constraint, and that will give us the last remaining unknown. Okay, so ILT equals particle solution plus the homogeneous solution. Okay, so that's our complete solution. And IL0 equals 0 implies that at t equals 0, this term disappears. And this E, the exponential term is 1, so we have K minus 80 over 3 equals 0. That gives us K. K equals 27, about. Therefore, we now know ILT completely. Minus 80 over 3 plus 10T plus 80 over 3 E to D minus 3 over 8 T Fs. So that's the solution. Let's also sketch that waveform quickly so that we have a better idea what the inductor current is doing. T seconds IL T amps. This is the origin. Okay. So we have two pieces. Here we have the constant slope piece or the particle solution, and then we have this homogeneous part. This can be called the transient part because as time goes on, this exponential will decay to 0, and then this will be less and less significant. And what the current is converging to is it's converging to the particle solution. Okay, so the particle solution is a line starting from minus 80 over 3. So this is minus 80 over 3 plus 10t, a line with slope 10. And then we have the decaying piece, the homogeneous solution, starting from 80 over 3. Decaying towards 0, and the overall solution is the sum of these two curves, okay, which looks like something like this. This is 80 over 3 e to d minus 3 over 8 t, and the sum of those two curves is something like that. This is our ILT. Okay. Let's move on to our second example for this lecture. So this is a circuit where the resistors are represented by their conductances. Not that these are not ohms, but moles. Okay. And we have a linear dependent current source where the control variable is the voltage for this resistor, 2 mole resistor, and we have a constant source. Okay, so this is, even though it has many components, this is nevertheless a first order LTI circuit because we have a single dynamic component, an inductor, LTI inductor, and the one port or the rest of the circuit that inductor is connected to is LTI resistor. Okay, therefore the overall circuit is a first order LTI circuit. Now in this circuit, the initial inductor current is given to be 6 amps, and what we asked for is not ILT, which usually is the case. Either we ask for VCT or ILT, but in this case we ask for something else in this circuit, another branch variable. Okay, we ask for the current I. What's IT for future times t greater than or equal to 0? Okay. Now, if you don't approach this problem in a systematic way, then you can easily get lost within equations, and in that case, it becomes really easy to make mistakes. Okay. So therefore, what we're going to do is we're going to approach this problem, as we almost always do, to a little bit complicated situations in a step-by-step fashion. Okay, so we're going to decompose this problem of finding this current into simpler sub-problems, and then we're going to connect the pieces one after the other. Okay, so what is our algorithm, or what is a meaningful way to approach this problem? Here's a meaningful way. Okay, first, well, we need the differential equation describing the circuit, okay, and by that usually we mean the differential equation describing the inductor current, or for the capacitor case, the capacitor voltage. Okay, so the first step, let's say we need to obtain the differential equation describing IR. Okay, so that's one of our goals, and for that we can work on this circuit, but it would be a little bit difficult, so it seems a better idea to first obtain the equivalent circuit seen by the inductor, our binary component. Okay, so we're going to obtain the Thevenin or Norton equivalent circuit seen by the inductor, then we're going to replace this chunk with that simpler topology, and using that simpler topology we obtain the differential equation describing the evolution of the inductor current. We have the differential equation, we have the initial condition. From there, we can figure out ILT. But we don't ask for ILT. Okay, we ask for something else. So we have to return to our original topology. And that we can do using this substitution theorem in the following sense. Once we know ILT, that means we know this current. Also, using the terminal equation of the inductor, we also know the voltage appearing across its terminals. Therefore, we can substitute this dynamic component either by a current source which provides ILT, or a voltage source which provides voltage VLT, and then make the circuit, okay, become an LTI resistive circuit. And then for that circuit, just apply your favorite method, node analysis, mesh analysis, or something else, to figure out the current that you asked for. Okay, so let's therefore write down our steps. Step 1, or step 0, depending on where you start counting. Find the Norton Thevenin equivalent circuit. Seen by inductor, or seen by the dynamic component. Okay, so This is where our inductor is connected to, and replace it or take it out and make this the 140, LTI raised to 140. And this we know has an equivalent representation, either Norton equivalent or Thevenin equivalent. Okay, and if you figure out Norton equivalent, circuit, and the details of figuring out is left as an exercise. You obtain this 30 amps for Norton current and 1/6 ohms for Thevenin resistance, or 6 mhos for Thevenin conductance. Okay, this is A, this is B. Then, with this simple topology, you reconnect the inductor here from A to B, and then figure out the differential equation, and then using initial condition, you figure out ILT. So let's do that in step 2. Step 2, using the equivalent circuit. Okay, we're going to find the inductor current. Find ILT. So here is our equivalent circuit once again. 6 mhos. Be careful about the units. In this example, they are given in mhos, conductance circuit. Okay, we have A, we have B, and here we have our inductor. And the direction of the current is from A to B. Okay. So that's why we're always careful about proper labeling. It tells us, or they avoid us from making some simple mistakes. Okay, this is IL, this is inductance. Okay. Now some of you can automatically write the differential equation, but let's do it in a formal way. By KCL, we're going to sum 3 currents and equate to 0. We're going to express everything in terms of IL or DIL, and that will give us the differential equation. First order, non-homogeneous differential equation with a constant right-hand side. It's constant because the input is constant. Okay, so minus 30 plus LDIL. Okay, it's voltage here divided by the resistance, or LDIL multiplied by the conductance. Okay, so we have 60IL. So that's the current here, and finally we have IL. And by KCL, the sum is 0. And rewriting this equation, we have 1/6 IL equals 5. Okay, our differential equation is here, our initial condition is here, and we know the answer. So ILT equals, so the particle solution is constant, this goes away, and therefore constant over 6 equals 5, particle solution is 30. Homogeneous solution is natural frequency z minus 1/6, therefore k times e to the t over 6, and then to determine that k, evaluate that function at t equals 0. Okay. 30 plus k equals 6, meaning k has to be minus 24. Okay. Therefore, ILT equals 30 minus 24 e to the minus t over 6. IL0 equals 6. Okay, so that's ILT. And VL is L DIL. L is 1, therefore the derivative of that function must be the voltage VLT. If you differentiate this, this 30 goes away because it's constant, and then what we have is minus 24 times minus 1 over 6 times e to the minus t over 6, and that's 4 e to the minus t over 6 volts. Okay, so this is the inductor current, that's the inductor voltage. Now, had we been asked the inductor current, the problem would have been over, but we're not asked for the inductor current, we're asked for something else. So we have to return to the original circuit. This simpler circuit will not help us at this stage. So step 3, therefore, is to return to the original configuration. Now, by substitution theorem, we can replace the inductor that appears between nodes A and B either with the current source, which provides the current of the inductor, 30 minus 24 into minus 2 over 6 amps. Or voltage source, which provides the voltage of the inductor, which is 4 e to the minus t over 6 volts. Okay, if you do that, this is what you obtain. Let me draw circuit here after the substitution. Moles, 6 moles, 2 moles, this is Vx, 2Vx, 2 moles, and now we have, instead of the inductor, a current source. Okay, the direction of the current source, same as the direction of the inductor current, which is pointing down, and this current source provides 30 minus 24 e to the minus t over 6 amps of current. Okay, and then in this now LTI resistive circuit, because we have no longer any dynamic component in the circuit, we can find I using our favorite method, either node analysis or mesh analysis or something else. So for the asked variable I. And the answer turns out to be I of t equals 4 plus 4 e to the minus t over 6 amps for all future times t greater than equal to 0. Now, we will move on to our third example. Now we have in this example a bank of capacitors. So we're going to be dealing with, for the first time, more than one dynamic component. But the topology is such that even though in general, if you have, let's say, 3 dynamic components, you would expect your circuit to be of order 3, meaning that the description will be through a third order differential equation, but in this case, because the topology is special, we will be able to work out the answer using our first order techniques. Okay. So here is circuit. So we have an impulsive input, and the capacitors, we're told, are empty, okay, initially. So capacitors are initially uncharged, so all the initial voltages are 0. And then what happens is this does what it does at t equals 0. Okay, this impulsive current will charge capacitors to some values, and then after that happens, this becomes short circuit. Okay, so the circuit becomes an input-free circuit, or homogeneous, described by a homogeneous differential equation. So what we have to figure out is first compute how this, or to what values, to what voltages this source charges the capacitors to, okay? And then, okay, one way to go is that, and then we're going to figure out what we ask for, which is I1. So find I1 T for T positive. Okay. Now we have three dynamic components. And this circuit is, well, for reasons that we're going to figure out in 202, the circuit is a second order circuit, and we asked for the current I1. Even though it's a second order circuit, we can solve it. At least we can obtain what we asked for using techniques that we developed for first order circuits. So let's go ahead and do that. Here is one way to approach the problem. So first, let's make use of the equivalence. Because of the special connection of those capacitors, seen from this pair of terminals, that bank of capacitors, or those three capacitors, can be represented, at least for the voltage current seen at the port terminals point of view, by a single capacitor. And we don't have to worry about the voltage of that single capacitor, even though it would have been easy, because everything is uncharged. Therefore, the initial voltage of that single capacitor will be 0. So this is what we want to simplify: the bank of capacitors. Okay. So let me label the voltage and current at the port terminals as such. This is 6F, 2F, 1F, okay? So everything is uncharged, therefore the initial voltage seen at the port terminals is 0. VC0 minus equals 0. And then this is equivalent to, we know from our earlier studies, a single capacitor, okay, whose initial voltage is same as the initial voltage here, which is 0. Okay, so we don't have to do it now. And then we have to be careful about picking the capacitance of that capacitor. So what we have is 2 and 1, they are in parallel. Therefore, this bank can be represented by 2 plus 1, 3 farad capacitor. And then we have 6 farad capacitor connected in series with a 3 farad capacitor. And we know that equivalent capacitance in that case is 2 farads. Okay? So therefore we have 2F as the capacitance, which we obtain by 2 parallel 1 and then series with 6. Okay, and now this is the initial voltage of this equivalent capacitor. Now what we have to figure out is what happens to the voltage, or what's the voltage at T0 plus due to this impulsive voltage source. Okay, so let's perform the analysis for this infinitesimally small interval from from 0 minus to 0 plus. Okay, now our aim is to find VC0 plus. Once we have VC0 plus, we can just replace this with short circuit and deal with the homogeneous case. Okay. Now the question is how we obtain VC0 plus. To find VC0 plus, we have to figure out the current here. Okay, if we can figure out this current by integrating that current, we can simply obtain the voltage, okay, at T equals 0 plus. Now, we don't have to be that precise about this current. All we need is the impulsive component, because we're going to do the integration in this interval from 0 minus to 0 plus, and all the bounded components of IC will not produce any contribution in the integration. Okay, so we have to figure out the impulsive component. To figure out that impulsive component, what we do is we replace the capacitor with any bounded voltage source. And since any bounded voltage source will produce the same impulsive component, why not choose the simplest possible bounded voltage source, which is short circuit. Okay, so in summary, to find the capacitor current, what we do is we replace the capacitor with a short circuit and compute the current flowing over this wire. 2 ohms, 4 ohms. Okay. Now, since this is a short circuit, clearly this 4 ohm has no effect, and therefore the current IC is the current flowing over this 2 ohm resistor, which is 6 delta divided by 2. 6 delta T over 2 ohms, and that's 3 delta T amps. That's our IC. And then VC0 plus equals VC0 minus, which is 0, plus 1 over the capacitance, 1 over 2, and then you integrate from 0 minus to 0 plus, ICT dt. So that equals, because this is 0, 1/2, 0 minus, 0 plus, 3 delta T dt, and that yields 3 over 2 volts. Okay, so at T equals 0 plus, that's our capacitor voltage. Now we can continue with our analysis for T larger than 0 for positive times, where this is replaced by short circuit. Okay, for T positive, what we have is this very simple homogeneous topology. Now, once that voltage source is short circuited, the 2 resistors become in parallel, and we have 4 over 3 ohms here, which is 2 parallel with 4. Okay, 2 ohms parallel with 4 ohms. Here, this is the voltage VC, and and this is our current IC. And equivalent capacitance, we compute it to equal 2 farads. Now for this circuit, we now know the initial condition. VC0 plus is 3 over 2 volts. Okay. Therefore, the solution VCT is immediately initial condition 3 over 2 times e to the minus t divided by the time constant. And time constant is the product of the resistance and the capacitance. So we have dVc plus 3 over 8, Vc equals 0. This is the homogeneous differential equation, which produces Vct equals the initial condition e to the minus 3t over 8 volts. And then Ict is CdVct. Okay. Capacitance is 2 times the rate of change of the capacitor voltage, which is minus 9 over 8 e to the minus 3t over 8 amps. Okay. Now we're very close to the final answer. Now all we have to do is we have to return to the original configuration. Here we have IC. At this point we know what this current is. Okay. And this current by KCL has to be divided between this guy here and this guy here. So this is I2 and this is I1, let's say. Then now we have to figure out what portion of IC goes to I1, because that's what we're asked for. Okay, so return to the original configuration. Positive. Now we have short circuit for the voltage source, because voltage source is impulsive and we're considering the case T is larger than 0. We have the resistors here. This is a 6 farad capacitor. This is 2F. This is 1F capacitor. This current is now known. It's IC. Okay. Then we have I1, this current. Let's call the voltage V1 of 1 farad capacitor, which also is voltage of the second capacitor 2F. And let's call this current I2. So what we know is, we know I1 equals C dV1. C is 1, so we have dV1. And I2 equals C dV2. C is 2, V2 is V1. Therefore we have 2 dV1. That immediately gives us the proportion of those two currents. Okay, so I2 must equal to I1. And IC equals I2 plus I1, therefore IC equals 3I1, hence I1 is IC over 3. IC equals I1 plus I2 by KCL, that equals 3I1, and that yields I1 equals 1/3 IC. And IC is here. Okay, divide that by 3 and you have your answer. I1 of t, therefore, must equal minus 3 over 8 e to the minus 3t over 8 amps.